Okay, welcome back. Today, we'll be talking for chapter 4, which is on discrete random variables. In particular, we'll be talking about probability distribution functions and binomial distributions. We'll start by saying what a probability distribution function is. Specifically, we're looking here at a discrete probability distribution function. This is a function, just like any other function, with inputs and outputs. Our normal functions that we're used to thinking of would be something like f of x equals x squared, perhaps. My input would be a number, my output would be the square of that number. That's a basic function. What we're dealing with here is a probability distribution function. Here, the inputs are the possible outcomes of an event, and the outputs are the probabilities of each such outcome. We know that probabilities have to be between 0 and 1, and for this probability distribution function, since it will include all possible outcomes, if I add everything together, it will total up to 1. Just like the Venn diagrams from the and or exercises, all of the probabilities need to add up to 1 because that's a 100% chance that something happens. We can make a table to represent probability distribution functions. Let's go ahead and make an example here. Let's suppose that x is going to represent the number of goals scored by a hockey player in a game. So we can look at the long-term outcome of certain games and look at the different probabilities. The first column in the table will represent x, and the second we'll say is going to be p of x, which is the probability of that number of goals being scored. Let's say that in this certain hockey player's distribution, the most number of goals scored in a game would end up being 4. And we've got 20%, 30%, let's say 25%, 15%, and 10% is the different probability distribution. So there's there's a 20% chance that our certain hockey player scores 0 goals, a 25% the chance that they score 2 goals, and so on and so forth. Notice that everything adds up to 1. We could have similarly put a 0.2, 0.3, 0.25, 0.15, and 0.1. This would have worked just as well. It's okay to put it as a percent or as a decimal. In either case, the total will be 100% here, or alternatively, 1 over here. Now, the most important thing that we can calculate from such a table is called the expected value. The expected value of an event where the outcomes are numbers is called the long-term mean. Basically, it's the number that we expect to get if we were to repeat this event over and over and over again over time. What we will do is for every single probability, we will multiply the value of that event by the probability of that outcome happening, and then we'll add them all up. It's kind of like where you take a mean of a frequency table, where you multiply each frequency by the number, except for the fact that we don't have to divide by how many there are, because we know that the total is going to be 100%. So that part's already taken care of. Let's find the expected value of the number of goals that we expect this hockey player to score. We can add another column in that we might call x times p of x. Here, we're certainly going to want to use the decimal number. 0 times 0.2 is 0. We've got 0.3 here, a 0.5. Here we get a 0.45 and a 0.4. So the total, if we add this all up, 3, 8, 12, 16, 1.65. What does this mean? Well, the expected value, or EV, for this hockey player is 1.65 goals per game. Now, of course, we won't say that in a certain game we expect them to get 1.65 goals. That doesn't make any sense. But over time, we expect that if they play, say, 100 games, they would get on average 1.65 goals per game. This is the long-term average. And the more times we repeat the event, the closer the average that we calculate from our sample will get to this more mathematically calculated long-term average or expected value. This is what's known as the law of large numbers. And I'll write that down here. The law of large numbers says the larger the sample, the more precise the statistics. The more people we survey, the more experiments we conduct, the more games we observe, the more times we do the certain experiment or the event, the closer our calculations based on all of the different experiments put together will be to the actual true probabilities and statistics. Now, let's take a look at one very specific type of probability function. A binomial distribution follows a binomial experiment. And let's talk about what that means. Bi means two, like for example in a bicycle, and nomial means number. So basically, there's two numbers. And the idea here is that we've got something that can only go one of two ways. Flipping a coin or voting for a president, ignoring independent candidates. All of these different things can either be one of two things, heads or tails, Democrat or Republican. There's two possible outcomes. Ideally, for a binomial experiment, we will have these two outcomes at a fixed probability. Flipping a coin is a really easy one, 50% heads, 50% tails. Voting for a president is more complicated because you don't know the exact probability that someone's going to vote a certain way. But ideally, we'll be able to come up with a probability from a sample. Maybe we sample 10,000 people and 7,000 of them said they would vote for candidate A over candidate B. So we can come up with a probability of 7,000 over 10,000 might be 70%. So we're getting some kind of fixed probability. We take the experiment and we do it a fixed number of times. We've got our sample size. We've been calling that n. We'll keep calling it n. We've got the two outcomes, which is the success and failure. We're going to let p be the chance of success and q be the chance of failure. It's not actually necessary that one of these outcomes be good or bad. We just have to define one of them to be success so that we have a name for it and we can assign our letters. Maybe we would say heads is a success and tails is a failure. Not that we really care which one it comes out, but we gave them consistent names. And then the most important thing is that each of these trials needs to be independent from each other trial. That way, all of the chances will be the same. And remember, the big thing we get for independent events is that you can multiply probabilities together in order to obtain the correct result. There's a couple of statistics that we can calculate, all of which we've seen before. We're going to let this capital X for the moment be the number of successes obtained in n trials. And this is why we define successes and failures, so that we only have to count up one of them. We'll let X count up the number of successes. We can calculate the mean and the standard deviation for X with the following formulas. The mean is simply the number of trials multiplied by the chance for success, which makes a lot of sense. If I flip a coin 100 times and 50% of the time it comes up heads, then I expect, on average, 50 heads. Very logical if you think about it. Standard deviation, there's a lot more computation that goes into this formula. I won't go ahead and show the derivation, but we see the same idea of a square root coming in. We take the square root of the number of trials times the chance of success times the chance of failure. You may also see the formula written NP1 minus P because P and Q add up to 1. This way you don't actually have to have Q written down. You can just only calculate P. We'll also use this notation here in order to symbolize binomial distributions more easily. For example, I might say that X, let's suppose it represents, X is the number of heads obtained flipping a coin 10 times. Then I might say it's a binomial distribution. I flip the coin 10 times, and each time there's a 50% chance that I succeed, that I get heads. In this case, heads is going to end up being success because that's the thing that I'm counting with my variable. The thing that you count with your variable, that's the successes. Let's do a more interesting example than coins. Let's suppose that we've got an amateur dart player. And I looked this up, about 25% of the time, an amateur dart player is able to hit the bullseye. Suppose in this certain tournament, they're going to go ahead and throw 36 total darts. Now, we're going to make a couple of assumptions here. We're going to make the assumption that every single throw is independent. So every single time that our dart player throws her dart, she has a 25% chance of hitting a bullseye, which means, of course, a 75% chance of missing. We're also going to make the assumption that she's going for the bullseye every single time. I don't know if there's more complicated rules for darts. I don't really play darts, but let's assume that she always wants to hit a bullseye. We're going to want to define a binomial distribution, define all the variables, find all the variables to calculate the mean and standard deviation. And then we're going to want to find the odds that in the entire tournament, she gets horribly unlucky and she gets just one bullseye the whole time. We'll start off with number 1 here. We have to define our variables. So we say let X, we could choose a different letter, but we'll keep going with X. Let X be the number of bullseyes. We can therefore, we're going to let it be a binomial distribution. Once again, why is it a binomial distribution? We've got a fixed number of trials, 36 darts thrown, a fixed chance for success, 25%, and every single dart thrown, we're saying, is independent. She doesn't get tired. She's not drinking anything. Every dart has the same chance of success. In that case, we would say 36, number of trials, 0.25, chance of success. And we can fill in our variables. N is 36, P is 0.25, and Q is 0.75. Next, let's calculate the statistics here. The mean, which is represented by this Greek letter mu, that's the Greek letter of a U, is pronounced mu. And that's the mean. It is equal to P times N. So that will be 0.25 times 36 is 9. Makes sense. She throws a bullseye about a quarter of the time. A quarter of the throws would be 9 out of 36. For the standard deviation, we'll need to take the square root of n times p times q. So square root 36 times 0.25 times 0.75. For this one, we'll definitely want to use our calculator. So first we'll do 36 times 0.25 times 0.75. That gives us, 1 second, 6.75. Then we'll take the square root of that, and we obtain 2.598. Remember, if it doesn't specify, 3 decimal places is probably a good amount. Third question asks us, what are the odds that in the entire tournament she hits exactly 1 bullseye? Now, this doesn't have anything to do with it being a binomial distribution. We can calculate this using our rules of probability. Remember that we've got an independent situation here. So we can just think of all of the different ways that she can hit bullseyes and then all of the different ways that she can throw the tournament. So our probability of 1 bullseye is going to be equal to the number of ways of 1 bullseye divided by the total number of outcomes. Now, let's start with the bottom. She's throwing 36 darts, and every single time there will either be a success or a fail. And we'll need to actually adjust this slightly because it's not equal odds. Let's go ahead and switch this up here. Oops. Okay. All right, there we go. Okay, so the probability of our 1 bullseye. If she's going to hit exactly 1 bullseye, she's going to have a 25% chance of hitting that bullseye, and then a 75% chance of missing, which we need to multiply 31 times because she's going to miss 31 times. So we can multiply this piece out here. So this will be a big number, 0.75 to the 31. And by a big number, I mean a very small number because of how much we're multiplying. So we've got 0.75 to the 31 times 0.25. So for the first piece here, we get 0.0000335. That is a 3 out of 10,000 chance that this would happen. But we do need to go a little bit bigger because this would be the odds that she throws a bullseye on a specific throw. Maybe that her first throw is a bullseye, and then there's 31 misses in a row. But then maybe her second hit is a bullseye, and that has the same chance of happening. And maybe her third hit is a bullseye, and that has the same chance of happening. And so we need to count this chance happening, which could happen 32 different ways. 36 different ways. Whoops, this should have been a 35. So our number will need to change because she's throwing 35, not 32. So we'll go ahead and multiply and fix that. It's actually another 0, 7, 9. So a little bit less likely here. We'll multiply this by 36 to account for that she could hit her bullseye on any one of the 36 throws, which gives us 0.000286. Or, in other words, there's about a 3 in 1,000 chance that on the entire tournament, she hits just one bullseye the entire time. Not extremely likely, but not so far out of the realm of the possibility that if it happened, we would have a suspicion that she was off her game. That's all we've got for today. We'll see you guys next time.